This is lecture outline 7, Roman numeral number 4, relationships involving delta H reaction. Well, in the previous lecture, part of this lecture, we went over how to determine delta H reaction using coffee cup calorimetry. Now I want to talk a little bit about the relationships between delta H for different reactions. And the first thing I'd like to say is that if the reactants and products of a reaction are switched, the sign of delta H reaction changes. And we've seen an example of that, and we'll put the same example here so it's close from us. So for the combustion of propane, we take propane plus 5 moles of oxygen, goes to make 3 moles of carbon dioxide, plus 4 moles of H2O. What we've said previously is that delta H reaction for this is negative 2,044 kilojoules per mole. And according to A, if we flip the reactants and products, we get propane and 5 moles of oxygen as products now. So we flipped or reversed the reaction. And delta H reaction for this is positive 2,044 kilojoules per mole. And let's think about what that means. What that means is that as we go on the top reaction from propane and oxygen to carbon dioxide and H2O, that process releases energy. And that energy goes from the reaction to the surroundings. If we then do the opposite process, so then in order for the reaction to occur, the process must take in energy. So that's the first thing. Second thing is, if we think of the potential energy of the positions, as complicated as this is, because there are so many atoms, protons, electrons, etc. involved, but whatever the potential energy here is, as these bonds change into the product bonds and molecules, then the potential energy is actually lower for the products, which means that the reaction releases energy. So delta H reaction is the heat energy per mole released. It is also the change in potential energy as we go from reactants to products. So because the reactants have more potential energy, the products have less. As you go from reactants to products, you release energy. That energy goes to the surroundings. And so that same amount of energy must be taken in for the reverse process, or for when the reactants and products are switched. Okay, so by that same way, if the coefficients in a chemical reaction are multiplied by a constant, then delta H reaction is multiplied by a constant too. So if the coefficients are multiplied times 2, delta H is multiplied times 2 as well. So now we'll go to 2 moles of propane plus 10 moles of oxygen and delta H from this top one is minus 4,088 kilojoules per mole. And in the same way, if we have twice as much reactants twice as large an amount, going to twice as large an amount of products, then we should expect to get twice as much energy released. In addition, so each reaction with its own set of coefficients, its own reactants and products, has its own delta H value. So please be aware of that as well. Okay, so those are the two relationships we need. We're going to use these relationships in what's called Hess's law. For Hess's law, the third thing we need to know about delta H is that if two chemical reactions are added, then the delta H reaction can be added as well. In this first example, what we're going to do is we're going to use Hess's law to calculate delta H for a reaction for which we don't know the value, based on two reactions for which we do know their delta H reaction values. And this is a powerful technique for finding delta H for reactions that are harder to do based on reactions that are easier to do. And so this is our second way to find delta H reaction. Okay, so Hess's law is a process. It is a bit of a puzzle. I enjoy puzzles. I don't know about you. So, but let me take you through the process of solving this puzzle. It goes something like this. I want to create this reaction out of the above two reactions. I can see that 2CuCl solid is also a product in one of my reactions, same as it is in the reaction I'm trying to make. So what I'm going to do is I'm going to take this reaction up here and write it down here just exactly like it is. With its delta H reaction minus 36 kilojoules per mole. Then I can see that I have copper, CuCl2, that is my reactant in the reaction that I'm trying to make and determine its delta H, and it's a product up here. That means that I'm going to have to flip the reactants and products and change the sign of delta H. Let me see, so the coefficients are the same. I'm keying off this because it's only in one of these reactions up here. Okay, so I'm going to put a minus sign there and a minus sign. The minus sign here just means flip reactants and products. Because the effect of flipping the reactants and products is to change the sign of delta H. All right, so write out the reaction, flipped. I try and line up my arrows when I can. When it's that helps me keep things a little more organized. Now, the things like chlorine that appear in both reactions, so I'm going to cross both of them out because they effectively cancel. One way to think of the reason they cancel is that whatever potential energy or energy in general is associated with chlorine as a reactant, that same potential energy is associated with it as a product. So we're not really canceling chemical species, we're canceling their energies. At least that's one way to think about it here. I can see I have two copper solids on one side and one copper solid on the other. So I'm going to cancel one out from each side, again, like canceling their energies. I'm going to add up what's left, and lo and behold, I get the reaction that I'm trying to build. Which is a harder reaction to do. So add my reactions, add my energies, and I get the delta H reaction for the reaction that I'm looking for. Let's see. So this bottom reaction is an endothermic reaction. It takes energy in order for this reaction to occur. Here's another puzzle. Here's another Hess's law problem. It says, calculate delta H reaction for the reaction here based on 3 reactions now. So this is a more complicated example. It's a more complicated puzzle. Same idea though. I'm going to work this one. It looks like this. When I look at the reactions that I'm given, I see I'm going to key in on this 2HNO3 aqueous, 2 nitric acids. Up here, I have 4 nitric acids, and it's the only place that nitric acid appears. So I have to make the coefficient of 4 into a coefficient of 2 in order to use these reactions to build my unknown. What that means is I'm going to have to multiply this reaction times half, and I'm going to have to multiply the delta H times half as well. Let me start by writing that. Half times 2 is going to be 1 N2. Half times 5 is going to be 2.5. Delta H reaction for this, 256 minus times 0.5 minus 128. One down, 2 to go. All right. Now, looking up here, let me see about NO2. NO2, nitrogen dioxide, only in one place here as well. On the top, it's a product. On the bottom, the one I'm trying to create, it's a reactant. That means I'm going to have to flip the reactants and products. Then I have a 2 here and a 3 down here. That means I must multiply it times 1.5 and do the same thing for the energy as well. All right, let's see if I can keep track of things. So this is going to be 3 NO2. Then I'm going to make 3 NO plus 1.5 O2. Delta H reaction for this process, minus 116 times 1.5 minus, I get 174 kilojoules per mole. Starting to see some of my oxygens canceling, which is good because oxygen does not end up in my overall reaction. Third one here. So there's nitrogens in a couple of them, oxygens in all of them. Only one nitrogen monoxide though in the third and first reactions. So let's see. So I need 1 NO here. I have 2 NOs. I'm going to, it's still on the product side, so I'm going to do that by half. Keep my fingers crossed that this works. If it doesn't work, I'm going to have to go get another piece of paper and start over again. Let's see. Now half N2. Oh, I hope this works. All right, so half O2 goes to NO. Half 183, 91.5. All right, let's add them up. See what we got here. I'm going to move over to green. I got an N2, and an N2. And I got no N2s on the other side. NO, N2O, NO. Well, let's see. Let's see, 2.5, 1.5. Oh, this one's backwards. Let's try that again. Minus, minus. Now I'm going to have this last one. It's going to be NO. And half N2 plus half O2. No, I just needed just plain 2. Yeah, that's it. So switch the sign. They're like little puzzles. Annoying little puzzles. All right, let's see if this works out. Now I have 2 on this side and 3 on that side. Good. I have 3, good. I have 2.502s, 1.5 plus 1. I have an N2 and an N2. Now all I'm left with is 3 NO2s plus H2O. All right. Goes to 2 nitric acid plus, is there an NO in here somewhere? 1 NO. A hard reaction to do, a somewhat hard reaction to solve for, and now my delta H for this final is going to be 128 minus plus 174 minus 183 minus 137 kilojoules per mole, and that looks right.